Okay, guys. Good morning. So what we are going to do today is going to be the continuations of waves discussion, and what we have in store for you today is one big property of waves that is actually it's fundamental properties that any waves in this universe is, I mean, they all have to follow pretty much. Okay. And what we are going to do today is we're going to extend the understanding in terms of describing waves using sinusoidal waves. And then we try to understand things that, I mean, on top of that sinusoidal wave, then we add things that we are going to learn today. And then we're going to see a couple of phenomena in waves. All right. And that allow you to do a lot more stuff with it. Okay, so that's what we are about to do today. Um, let's start with this. And it's a very simple one. And the good thing is there's still no more calculus or anything. So within this second module over here, I think you guys are pretty much safe with algebra. It's pretty good, right? You only just add, subtract, multiply, and maybe the most complicated one is the sinusoidal function. That's what you have to do. Okay. All right. So the first thing that we're going to do today, we call superpositions of waves. And this one is based on this principle right here, is the superposition principle. The idea is super simple, guys. So what you have here is if you have two waves, and if it's travel in opposite direction in this case, all right, even though it doesn't have to be in opposite direction, but this one is the most obvious one. And then as you can see, if you can describe first waves using some function y sub 1, and the wave number 2 is a y sub 2, and then of course wave never stops, right? So they are going to actually travel, and they're going to pretty much meet at some point, and then eventually they're going to just keep moving. So what happened is during that meeting, okay, so in the midpoint over here, so you might wondering like what will happen to the combined wave. So you want to have them combined. The answer is super simple, guys, and you will be amazed. Just add them. That's it. All right. And this principle, we call it the superposition principle. So what it means is if you have if you have two or more waves meeting at a single point, what you can do is just you can find the resultant waves by just add them all. And it's a linear addition. So it means you just sum them all. So in the case that if those two waves, once they passed, and it actually is not passing or anything, it's just no matter when, no matter where, actually they are just y1 plus y2 all along. It's just that. Okay. But maybe we just pay attention during the time that they are actually at this around the same positions. But overall, they are just a combination of the two all the time. Okay. And the reason that we can still use this one is because we are talking about linear waves. When I say linear waves, it means it's followed the superposition principle right here. 1 plus 1 equal to 2. So the reason that I have to emphasize, sort of like talk about this a little bit about the linearity of waves is because there are waves that are not linear. So we call those like non-linear waves. All right, they are. All right. So it doesn't mean that all waves has to be linear all the time, but there are some special conditions that if you generate waves in that special things, and then when they combine, and because of the environments are different and everything, they might not combine linearly. So what we have over here is for just a general waves, just any waves, just regular waves, electromagnetic wave, light wave, or whatever waves, water's waves, strings, wave on a string, everything, we can still say that they are linear. So that means they all follow superposition principle. Okay. So maybe I already talked too much about this, but that's what it is. And that leads you to two extremes. There are two extreme possibilities. So the first case we already saw. What you saw over here is once they combine, you get a bigger, see that the end results end up with a bigger waves. That's because you can think of it like the Y1 might have like A1 amplitude, Y2 might have like A2 amplitude. So when they combine, that will be at some point that they actually have to combine those amplitude. And then the maximum amplitude, the maximum displacement possible gets even larger than each waves individually. Okay. However, there might be a case that the displacement is actually in the opposite direction. But because of the superposition principle, that is fine. At the end, you just get, there are still summation of the two, but at the end, you get the difference between these two amplitudes, right, or displacements. All right. So that means there are two extreme cases. The one on the left, we call it they are combined constructively. Okay. And the right one on the right column there, we call it they combine destructively. And the combinations of two or more waves, we call this phenomena the interference. Okay, so in conclusion, the interference is whatever, whenever that you have more than two waves, try to combine into like a resultant waves. Okay, and based on the superposition principle, the resultant waves is simply the summation of those waves. But we can categorize them into two extremes. One could be the one that once they combine, you get a bigger displacement. At the end, you call it the constructive interference. But on the other hand, if you have two waves moving in the opposite direction in displacements, so once you combine, you have cancellation effect. So we call that a destructive interference. Does that make sense? Okay.
Okay.
So that's pretty much the conclusion. But overall, everything is just under this. It's superposition principle, and be done. All right, cool. That's how simple it is. And the good thing about this one is it seems like the internet seems to be better now. I don't know why, but it seems like it's more fluid now. Okay, so let's apply the knowledge that we have already sort of like studied week before about the sinusoidal waves. And then now we are trying to combine them. Okay, sounds like a good plan. Okay, so what we are going to do here is just quick reminder, guys. I think you guys know how to read this already. So you know how to read wave function. So let's give you the first wave, y1. You know what is the amplitude, that's the A. The numbers in front of x, that will give you the wavelength because the k is the wave number. So this one is 2 pi over lambda. So you can extract lambda out of it. The omega is just the angular frequency. So it's a 2 pi over f or 2 pi over period, no problem. The sign in between is telling you that this wave is traveling in the positive x direction. Cool, that's done, right? So everyone with me so far? So now you know how to read this thing. Now we need another wave because we're going to get a combination of two waves. So let's introduce to you the second waves over here. And what you have here is now same amplitude, cool. Same wavelength, no problem. Same frequency, yes. Same direction of movement, yes, positive x direction. So you have exactly same type of waves, except now you get an extra phi, which you guys remember, this is just a phase constant. So it's just like taking the original wave and then you just slide it left and right, depending on the value of the phi. Does that sound good? Okay.
Okay.
So let's consider what happens if you pick different value of this phi and see how it goes. But at least what you are seeing over here is you're trying to look at the interference of two waves that is actually traveling in the same direction. Okay, so that is fine. Okay, just go ahead. So what you have over here is, let's get you a very easy one in the case where the phi is 0. Let's go for it. So what happened when phi is 0? It means the two waves are exactly the same, right? Because it's exact same equation. Oh, actually, it's even better. I should color code it here, guys. Sorry. Yeah, let's do the first one to be blue and the second one to be green. So that's the A, the K, the omega. Everything is right there. Okay, positive x direction. So it means now the first wave, which is in blue, and the second wave, which is in green, combines, but because they are oscillating in sync, you guys with me? Because there's no phase difference, the phi is 0. So that's where the first figure is showing right now. So the green and the blue are actually on top of each other. They are like completely overlap on top. So that's and the green is actually here as well. Okay. So what is going to be the resultant wave? You just add the two together. And the red one was just a combined wave. Cool?
Okay.
Easy enough, right? But this is exactly what you can see now, that the amplitude of the resultant wave now extend two times. Is twice as big as the original. So that's why we call this an constructive interference. Plus, Because if you look at the rhythm of the movement, okay, don't forget wave never stop. What you're seeing over here is just taking a snapshot, right? Because it's frozen in time. But actual wave has to travel. It's just going from left to right because it's moving in the positive x direction, right? Just keep going, keep going. But if you look at one particular point, so maybe, for example, if you are standing right here, yeah, let's focus on here. Then what you're seeing over here is this movement is going to go up and down, up and down, up and down, keep going up and down like this, right? So that means the blue and the green waves are actually moving in phase. So they are moving in sync. They are synchronized in movement. So that's why the resultant wave is double the displacement. So you get twice the amplitude. Cool. All right. No problem. Now let's try another type. Let's say if you adjust your phi to make it, well, all right, just having more fun with it. Let's try 180 degree. So that's when you pick 180 degrees. So it means you slide the green wave is actually half a wavelength from the blue. You guys with me?
Okay.
Because you pick the phi to be 180 degree or a pi. So it means that's half the wavelength. Or if you speak in terms of the period, so that's half the period. So if you talk about in terms of the cycle, it's half the cycle. Okay, so that means if you look at this one, this is the case. So if the blue is actually starting from wherever it is, the green has to be shifted by half the wavelength. So now you can see that the blue and the green are oscillating perfectly out of sync. Once when the blue is at the positive max, the green will be at the negative max. And then it's going to oscillate back and forth in the opposite direction at all time. So we call this the out of phase, the opposite in phase. Okay. And the resultant wave is now going to be a perfect cancellation over here. So this is the case of the destructive interference. You guys with me now? Cool. And then at the end, can I pick some other value of phi? Well, yeah. For example, you might want to try like 60 degree. So when you want to try 60 degree, what happens? Now it's going to be tougher for you to do it using just like a visualization tools or just doing the graphing. So what we are going to do is we're going to use a little bit of trigonometry. Let's give it a shot here. So we already said the resultant wave is easy. It's just the combination of two waves. I mean, in this case, we have only two. So we just add them together. Okay. And then this is what you have. You just add and add. Just add two waves together. Okay. And there is a question comes in about the units of the phi. The phi, if you plug it in here, it has to be in the radian units. Yes. Okay. But we can speak interchangeably between the radians and degree because we know pi is always 180 degree. Yes. Okay. But if you want to plug it in here and make it look sort of like nice and uniform in terms of the unit, it's supposed to be in radian. Okay. Very good. All right, now come back here. So now all you need to do is just add these two together. And we have already seen there is a property that you can convert or sort of like change the addition of two trigonometric function into the product. And then you can use sine A plus sine B equal to 2 cosine the difference over 2 times the sine of the sum over 2. Let's give it a try, shall we? Okay, so what I'm going to do is and just add them together. So what we got here, I'm going to work in red over here. So you get A, I can pull out a common factor. Okay. And then I have 2. So I put 2 in the front. And then what I am doing next is just starting with the cosine. I'm taking the difference divided by 2. Okay. So let me do in full over here so you guys can follow. So this is what I'm going to write it out here. Pretty good. Divided by 2. That is the cosine terms over here. Now I'm follow this with the sine term, which is just the sum over 2. So just do kx minus omega t plus kx minus omega t plus phi, the whole thing divided by 2. Make sense, guys? So far so good. Haven't done anything acrobatic here. This kx minus omega t cancel in the cosine terms. And this thing here, in the sine term, you have 2 of the kx omega t. So once I divided by 2, then I get back the kx minus omega t. So I have only thing left that has to be divided by 2 is the phi. Okay, so far so good. So what you got at the end is this. So 2a is there. It's fine. The cosine, I have left with the negative phi over 2 in here, but cosine of positive or negative doesn't really matter. So just plug it in cosine phi over 2 here. And the last term that you got is going to be kx minus omega t and phi over 2. You are done.
Okay.
So far so good. All right, now look at this, guys. What are you seeing here? So everyone know, Ajahn, this is the resultant wave. This is the combined wave from Y1 and Y2. There's no big deal. But if you just read this one, just like, hey, I just present to you these waves. What kind of wave is this? Oh, maybe don't need this. What kind of wave is this? Well, okay, Ajahn, I can read this, right? I know I can. So what you have over here is K is still the same. So it means it's the same wavelength. Omega looks exactly the same. So it means it's the same frequency as the Y1 and Y2. All right, you shift the wave a little bit, sort of halfway the phi. But then we already discussed this. Whatever come in front of this sine factor over here, you call this amplitude. Is that right? So that means for the resultant wave that you are looking at this point, your amplitude depends on this value here, 2a cosine phi over 2. And this is what happens in the two cases before. See, when phi is equal to 0, your amplitude is 2a cosine 0, which is cosine 0 is 1. So that is 2a. And you already did when phi equal to pi. So you get when phi is equal to pi, then you have 2a cosine pi over 2. You guys with me? And cosine pi over 2 is what? 90 degrees. So cosine 90 is 0. So that is 0. Perfect. See? So this is the case that you can determine the amplitude of the resultant wave. When phi is equal to 0, that's your first case right there. You just say, okay, the amplitude now is 2a. When you pick phi to be pi, that is your second case over here, you can say, oh, now your new amplitude is 0. So you get a perfect cancellation there. And now you can answer the third case. If you pick phi to be 60 degree, all you have to do is just substitute that 60 degree in here. So what you can tell right away is the amplitude that you're seeing over here is going to be 2a cosine phi equal to 60 is pi over what? Over 6? It's, over 3. So you divide it by 2. So it's going to be pi over 6 right there. Isn't that cool? All right. And with that, then you can determine the resultant amplitude of the combined wave. Cool. Plus, as you can see, because now you already saw that the resultant wave has the phase of phi over 2. So look at the resultant wave here. Does that make sense to you guys? Look at the blue. The blue is here. Let's look at the peak. I think that's the easiest point to look at. Peak of the blue is there. Peak of the green is here. And then you can see that the peak of the green is just right in the middle. But you already know that these two are separated by 60 degrees. So that means the blue and the green is going to be separated by 30 degrees, which is perfectly here. That's what it is, 30 degrees. Cool, done.
Okay.
Okay, so the point of this slide is to showcase that how easy it is for you to get a combined wave. Okay, it's just simply y1 plus y2, and even have you have even more like 2y3, y4, y5, you can just add on top of this one. The algebra would just get crazy, that's all. But the concept is just simply applying the superposition principle. Just add them all. Nice. All right, any questions? So silence is good.
Okay.
Silence means good. Okay. All right. So that's what it is. All right. And that's how easy it is to apply this superposition principle. And you automatically learn the interference of waves. Perfect. Okay. Now, what kind of application that you can think of when you look at this sort of like interference of waves? Okay. One thing that I can think of, and I think that's very relatable nowadays, is I don't know, you guys have ever used that the noise canceling headphone? Yeah, the noise canceling headphone is exactly this dude right here. So in the noise canceling headphone, you will have a like a mini microphone in there. That microphone try to listen to the ambient sound. And once the sound gets into the microphone, there is a chip that flip the phase 180 degree and it's generate that sound again. So think of it like you take in the sound and you shift it 180 degree and then you just pass through. And then when that get recombined with the normal ambient sounds, so that means you have like a sound that has been shifted by 180 degree, gets to your ears, and that get cancellation. So that's why there's no noise get into your ears. That's what it is. All right. So that's, I think that's one application that everyone seems to be able to at least can, get, you can own it. You can own like a a device that can do like a destructive interference for you. And the waves that we were talking about, that was the sound waves, right? But it works for any waves. It works for any kind of waves. Okay. All right. Now, think realistically. All right. Everything is cool. You know how to draw, or you know how to write the mathematical descriptions of waves. Everything is good. You can do the combination, do trigonometric stuff, and everything is good. But in reality, who will measure the wave form or the wave function, right? Does that make sense to you? It's like in reality, if you talk about sound, you're not gonna like try to measure like, how molecule of air is kind of oscillating or no this stuff, right? When you talk about sound, you probably want to I just want to hear it like noise canceling headphone. I want to see the final effect of it. So for you to be able to do some observations, to do some experiments on the stuff, you probably don't want to really get down to the like, dirty business of doing like the sine and cosine, try to figure out what is the value of phi like directly like this. You must have some other thing that you want to measure. And the easiest thing to measure is this, is the distance. That's something easy because you can grab like a ruler, you can have like a meter stick, and then just make a measurement, right? That's easier than measuring like sine and cosine function and try to figure out the phase. So I will just give you a scenario. What could happen in real life? So this is what it is. Here, the textbook used this setup, which kind of like maybe a little weird for you, but it's very doable in the laboratory. So this is what you have. You have a speaker. The reason that I pick a single speaker, I just want to make sure that the sound coming out of it is exactly identical. Okay. Now you split this speaker into two paths. Okay. So just like the two that you saw before, you can think of it like the upper path that the sound travel. Upper, let me use the blue. There's, oh, the blue is down here. The R1, so the wave had to travel in the bottom path here to reach the observer's ear. And now there is another sound coming out, and it has to travel R2 to reach the observer ears. Yeah. So far, so good. So now think about it. So this is exactly when you think of like you have two waves, and eventually one wave travel with the distance R1, another wave travel at the distance R2, and it's eventually is going to combine at the point of receiver. Okay, cool. So scenario is already set. Now here comes the question. And I think this one is easy to answer. What happens if R1 and R2 are exactly the same? What kind of interference that you're supposed to receive at the receiver? What do you think? Well, okay, Adan, because they travel at the same distance. So that means at the point of the receiver, the wave will still look exactly the same. Does that make sense to you? Because it has already gone through exactly the same distance, so there won't be any difference whatsoever. If the wave number one has gone through like 3 cycles, wave number two will have gone through 3 cycles also. So that means once it reaches the destination of the receiver's ear, you're gonna see these two waves still oscillating up and down like this. Does that make sense? So that means at the receiver's ear, you're supposed to get a constructive interference. Okay, and the way to sort of like summarize this very easily, you can say R2 minus R1 is just 0. And I can take absolute sign because I mean, I don't care which one travel longer or smaller. We just say they travel at the different distance of 0. They travel at the same distance. Cool, so far so good. Now think about it. Let's say if the upper path is a tube that is movable, so that means I can actually move this tube up and down. Let's say just up then, all right? Let's say, so that means if I move this tube, the upper tube up a bit, and it turns out the distance R2 gets extended. So the wave number 2 get detour, it had to travel a longer distance before reaching the receiver's ear. You guys still follow so far? But let's say that the R2 turns out to be one more of a cycle than the R1. So what I'm saying is, what if you translate that tube up and eventually the distance traveled by the second wave, the R2, the upper wave, is perfectly one wavelength away. So has been detour for a perfect one cycle. So what happened at the receiver's ear? Nothing. Because at the receiver's ear, he doesn't really know anything, because the wave from those two waves eventually will look exactly the same. You guys with me? Because it's already perfect, get translated perfectly one full wavelength. So whatever that receivers can observe, it's going to look exactly the same. It's still oscillating in phase. Everything is being oscillated in sync. So you still get a constructive interference anyway. You guys with me? So in this particular case, what you have over here is the distance difference is perfectly one wavelength. You still get a constructive interference. Now you can start thinking about it. Okay, now I kind of get it, John. If I move up one more step further, eventually the R2 is greater than R1 by 2 perfect wavelengths. What will happen? Nothing. At the receiver's ear, you can still see those two waves oscillating in sync. You guys with me? It's like, okay, there's no difference. So that means when the R2 minus R1 is 2 of the wavelength, you can still get the perfect constructive interference anyway. And this list can go on and on. You can get the difference of 3 lambda, 4 lambda, on and on. So the conditions that eventually you're going to get a constructive interference is only saying that the path difference, here we go. This, we can name it the path difference. And you can say R1 and R2 is just a path length. It's just the length of the distance, the length of the distance, yeah, the length of the distance that is a distance that the waves get travels before it reaching the destination. Okay, so what you have over here is the conditions that eventually lead you to a constructive interference is simply saying that the path difference has to be multiple of lambda. That's it.
Okay.
Does that sort of like get to the point here? I think you see what I'm trying to get at next. So you can come in halfway. Let's say at the time that you try to slide the tube up, instead of stop at perfect one wavelength, what if you cut short and then stop at halfway? So let's say, what if your R2 minus R1, and then I put absolute sign, so I don't care which one is bigger, and that doesn't matter. But it turns out to be exactly half the wavelength. So what will happen at the receiver's ear? You can guess, yeah? It's gonna go opposite like this, right? Because one of the wave gets translated half the cycle. So now you get an out of phase setup. Then the oscillation is now out of sync. It's perfectly opposite in oscillation. So at the end, you get perfect cancellation there. So this is the first condition that you're going to get a destructive interference. Does that make sense? And once you have that set up, now I can slide this one wavelength extra because if you already started out with like half the cycle away between each other, if you add one full cycle to it, you still get the destructive interference anyway. So that means you can have this with an extra lambda to it, you are still in the destructive interference condition. Make sense? Yeah?
Okay.
And now you can play with it. I can move one more. on top of that, okay, don't forget we started out with the lambda over 2, right? So once you have that, you can add extra wavelength to it. So now you have 2 lambda extra on top. You still get the destructive interference anyway. So in the end, what you can get is all you have to do is just make the path difference to be multiple of wavelength with an extra half a cycle on top. You will get to the destructive interference. Cool?
Okay.
All right. And then I can sort of like put this into like a compact notation over here. Just say it's 2n plus 1 times lambda over 2. And if the path difference meets these conditions, you will get a destructive interference. And we are pretty much done.
Okay.
It's like doable, I think. All right, this is not too bad and it's quite understandable. But the thing is, now you might have to go back and forth between these two. When I say these two means the one that you try to speak in terms of the phase right here, right? Everything that follow the sine and cosine, this is the phase, the pi, 3 pi, whatever pi. And in reality, you have to measure this path, 1 or 2 and this. So what kind of like linkage or what kind of like the connections between the actual distance and the phase? The answer is very simple and you guys know this already. The answer is, here we go. Think about this. Every time that you talking about one perfect wavelength difference in distance, it's equivalent to the wave has already gone through one complete cycle, correct? And we already know that whenever you complete one full cycle, the angle or the phase of the waves has already gone through 2 pi. Does that make sense? So that means you know that every one full lambda, that will be equivalent to 2 pi of the phase difference, yeah? So from now on, if you have whatever value of the distance, it doesn't have to be exact wavelength, but it could be any value, and that value could be like delta R that we are discussing right now. How can we turn it into the phase? That's easy. You just take the ratio and multiply by 2 pi. Does that make sense to you? Is it good?
Okay.
Right? Because it's just like, I don't know, have you done like, I don't know, in Thai it's called เทียบบัญญัติระยาง I don't know where this word comes from. I still cannot find the root of this one, but I think in the, and for those of you that do the international curriculum or this stuff, I don't think you have this word. I don't know. Or if some of you knows what the เทียบบัญญัติระยาง is, then please tell me. I try to figure out this word, but I cannot find it. But anyway, the point is you just take the ratio, right? Because you know that every lambda is equivalent to 2 pi. So what you want to do is, what about you have the distance of only delta R, or you can put X, you can put A, you can put whatever, then it's going to be equivalent to what value of the phase. Does that make sense? Yeah, this one. So it's just a proportion, taking the proportion, or you just take the proportion of that. So the phi that you want to figure out is just going to be the delta R over lambda, and you multiply by 2 pi. And that's what this expression is about. And you are done.
Okay.
Cool. All right. So think of it very easily. Like you want just to convert between distance to phase. It's simply saying that every one wavelength, that's 2 pi. So if you have just a fraction or just, you know, just a proportion of that wavelength, you just take the ratio of that distance over lambda, and then you multiply by 2 pi. Yeah. All right. So it's just a proportion calculation there. อันนี้อาจารย์พูดรู้เรื่องไหม Okay. All right, guys. So I think maybe the easiest way to try this one is just look at some exercises and then see how this thing get applied. Yeah, shall we? Yeah. So let's take a look. Okay. So let's take a look at the first example. So you have 2 traveling sinusoidal waves. And I hope by this time you guys sort of understand that waves has to be 2 variables function. Waves never stop. It's going to be something moving all the time. So it has to be like baked into your head when we talk about waves. Okay, waves are described by the wave functions below. So you have y1 and y2, and I think there's a typo here. There's no tau here. It's just t. Okay, now when you look, like just take a glance, look at this one about John, that is good. Oh, okay, that's nice. Same amplitude, same wavelength, same omega, same frequency. There is just a phase difference a little bit. It's fine. Okay, just a little bit off, but that's okay. So what is the amplitude of the resultant wave? You have already seen that, but then you just add these two together. So y, let me call y total, okay, is just going to be by superposition principle, just add them together. And you have already seen this is just two sinusoidal waves summed together. You're going to get the final result to be 2a cosine the phase difference over 2. And then you get the sine of exact same type of waves, okay, plus phi over 2. Actually, it has to be minus, but that's okay. Right, there you go, minus phi over 2. Yeah. All right. But anyway, you don't have to memorize this formula. All you have to do is just take this y1 and y2 and just add them together. That's what I'm doing. Okay. So let's add them together. So you get 2 times 5. Okay. And then you do the sum, the cosine. Okay. Start with the cosine. Cosine of the difference divided by 2. All right. So, the formula on top is just a reference, but that's where you want to get to. So you just take this argument over here, take the difference, and then divide it by 2. When you take the difference, the whole thing cancel. You're left with just this 0.25 pi and then divided by 2. So that's why I get 0.25 pi divided by 2. See, exactly the same as what you saw up here. So far, so good. Yeah. All right. Now, and the term of the sine, you just say it's a sine, and then it's going to be the sum over 2, right? So you just add these two together, divided by 2. So this whole term here, add and then divide by 2, you get the original back. So it's going to be 2 pi x minus 12 pi t. And then, of course, this term is going to get divided by 2. So minus point, okay, let me put like minus pi over 8 then. All right, here we go. And that's it. What is the amplitude of the new wave? Whatever comes in the front, that is your amplitude. So the new amplitude, it's like the resultant amplitude is going to be, oops, sorry. I think I put the box a little bit too small. Here we go. There you go. The amplitude of this one is going to be whatever comes in front of that sine function there. Cool. So the answer for part A, so the new amplitude is 10 cosine pi over 8. Done. Okay. And what is the frequency of the resultant wave? Oh, Achan, it's no problem. I can see that the numbers comes in front of t that give you omega. So the omega of the resultant wave is 12 pi, and that is just 2 pi f. So f is just 6 hertz, and you are done.
Okay.
See? So I hope that now you know how to read the waves function, you know how to manipulate the waves function, and with the superposition principle, wow, it's just easy. Just add them. And you don't have to worry of anything. You just add them. Okay, be done with. Cool. So far so good. All right, try one more. There you go. All right, now this is more realistic one. So you have a pair of speakers placed 3 meters apart and are driven by the same oscillator. So just guarantee that the sound coming out of these two oscillators are identical. The listener is originally at point O. Okay, so that's at the center, which located 8 meters from the center of the line connecting the two speakers. Now the listener then walk to point P. So he walks up a bit, which is a perpendicular distance 0.35 meter from point O before reaching the first minimum. So that means starting from point O, eventually once he reaches point P, it gets sort of quiet. That's the first minimum. That's what it says. Minimum means no sound, no sound. So what is the frequency of the oscillator? Cool. So first thing first. So you can sort of like look at this one and understand this one saying that, Ajahn, when you are at point O, the distance traveled from the two waves are exactly the same, right? So when you start from point O, the sound coming out from the first speaker, the sound that coming out from the second speaker reaches point O by going through the same distances. So, whoa, what you get from point O over here is, well, Ajahn, at O, delta R is, okay, I can put like R1 and R2, okay? It's gonna be 0. So that means what you get over here is gonna be a loud sound, and that means it's a constructive interference. Does that make sense? There you go. Nice. Now you moving away from point O by walking up. So the conditions will start to change a little bit because now the R1 will get, in the different value, the R2 will get a little bit longer. Okay, so now you have some non-zero path difference. However, once you reach point P, what happened, guys? You reach the first minimum. So that is the indicator saying that at P, the delta R must be exactly what now, guys? Can you guess? Okay, you're supposed to get to the point where the path difference is exactly half the wavelength. Cool? Yes, because that's the first time that you're hearing no sound. That is the first time that you're going to get a 0 resultant wave, nothing. And that is no sound. And that is the destructive interference. Cool. All right, and that's it. That's what you want. So all you have to figure out is what is the R2 and R1, and you can figure that out very easily by looking at that triangle over there. So to get the R1, that's fine, John. When you look at the upper right triangle over there, the R1 is going to be square root 1.15 square plus 8 square. Yeah. And same thing happens for the R2. You look at the bottom right triangle over there. It looks pretty ugly. My bad. Okay. Square root 1.85 square plus 8 square. So you just apply Pythagorean theorem there. So, okay. In conclusion, you will be able to figure out the numerical value of R1 and R2. Just plug it in there. So at the end, what you get is lambda is going to be twice of that R2. Okay, I know that R2 is going to be larger than R1. All right, but I put everything under absolute sign anyway. And once you get that lambda, the frequency is always V over lambda. We already knew this. All right, and then you can apply the speed of sound in whatever here. It's just a regular air, nothing. Then you can apply like 340 meter per second, and then you divide it by wavelength that you got from your calculation there. There you go. Just plug it in here, and you are done.
Okay.
Does that make sense? Okay, so this is how how simple it is to apply once you understand the underlying sort of like the components that you need to use in your analysis of interference of waves. Okay, and actually I can explain just a little bit more what happens next. So I have like a bigger figure over here for you to analyze here. So as you can see at point O, that's when you sort of like get the guarantee to have the constructive interference, right? And once you reach point P, we already saw that that is the first minimum. So that means at this particular point, your delta R is perfectly half the wavelength, correct? Now, what happened if I keep walking up, guys? Just keep walking up. So when I walk up, eventually I will reach another point. Let me call this like point Q. At that point, you will see that eventually you're going to get, the distance traveled by the first wave and another distance traveled by the second wave. Eventually, it will reach another conditions of a constructive interference. So what I'm saying over here is, once you reach point Q, the delta R will eventually get to the lambda. And at this point, at Q, you're going to get a loud sound again. Does that make sense? And if I keep walking up, eventually I'm going to reach, let me call this like point M. So you do the same thing again. You just have to measure the distance traveled by the first wave, distance traveled by the second wave. But then now you can see that the path difference now eventually will reach to the condition where your delta R is going to be 3 lambda and a half. So you add extra lambda on top of it. So you get the quiet sound or hear nothing again. And if you keep walking up again, let me call this like point N. So over here, you just do the same thing. You calculate the distance traveled by the first wave, and then you look at the distance traveled by the second wave, take the difference, and then you will eventually reach the point where the delta R will be multiple of lambda again. So now it's going to be 2 lambda. So over here, you will hear the loud sound again. And these patterns will repeat pretty much forever.
Okay.
It's just like, no need to clap there, but that's what it is. So you start from the midpoint at O, that's a constructive interference. Now you move away from it, you're going to reach the first minimum, that is your first destructive interference. So that is the indicator that your path difference is half the wavelength. And then you keep walking up, it will just meet the condition that you come back to the full one complete cycle again. So you hear the loud sound again, and on it's going to alternate back and forth. Okay. So you can do this, and then you get like a full pattern of the space around these two speakers. There'll be some point where things are quiet and some point things are loud. And in the middle, there'll be somewhere in between. All right. And just for in the future, even though we don't do this in our class, but if you change this into a light wave, a light. So if you talk about light wave, then that is fine. Instead of having hearing a loud sound, you're going to see a bright location. And instead of having like no sound, you will see a dark region of the light. Does that make sense? So if you turn this into light wave, then all you have is going to be the bright and the dark spot, or bright and the dark area on your screen, or on whatever you use to observe your lights, interference of light, pretty much. Okay, cool. All right, guys, and that is it. It's done for this particular story about interference that's having two waves traveling in the same direction. So this is a good place to stop here. And after the break, we'll do one more kind of interference. And that will be something that when waves travel in the opposite direction. Sounds like fun? Okay.
Okay.
All right, guys, take 10, and then we'll see you after the break. Yeah. And what we will see next is trying to apply the concept of interference, which based on the algebra based on just the superposition principle. So there's nothing much in terms of the the process of calculations. However, the phenomena that you're about to see is very, very, I would say, it's simple at the end, but to understand this one perfectly is kind of like confusing at first. The reason is because if you look at this one, it's like, okay, John, it's maybe some visualization and other stuff and things going on over here. But then what we want to look at is how can we actually understand this sort of like, I don't know, you call it like it's not a real wave, of course. I mean, the wave cannot be split in like a loop like this. So there must be some meaning to it. And what does it mean? Okay, so what I am going to explain to you, and the second half of this lecture is going to be kind of light. You just like sit back and relax. Don't need to do anything much. It's just hear me out, okay?
Okay.
And see how it goes. I don't know, will this work or not, but I hope it will help you understand the scenario that we have right now. So what I'm trying to talk to you about is this. Let me bring you guys back a bit, back in the day of wave on a string. Okay, sounds like a good plan. So this one, because everyone can relate to very easily. So what you have over here is this. If you have a wave generated on a string, and let's say I have that string fixed at two ends. So it means maybe I just tie on the walls and have another walls opposite to that, and then it's just sort of like have those strings put on there. Or you can think of this one as just like a string instrument, like a guitar string or a bass string or whatever. Yeah? You guys sort of familiar with that. So you have some tension on it, you have something on it, and once you plug your finger on it, you can generate wave traveling inside that string. Okay, so far so good. So now let's say if we consider just a simple a pulse, let's say I generate a pulse of wave on this string. So this pulse will just travel, let's say going from left to right at this point. But once it reach the end, it's gonna get reflected. So this pulse will get reflected back. Yeah. But because of the action reaction at the wall, the reflection of this will just come out in the opposite direction. So it means if you get the head in, the tail will come out. If you come in up, you can come out down. So it's just we talk in terms of the phase. The reflected wave is going to be 180-degree phase difference. But that's not the key point. I mean, that's just a story that just I'm telling you that is what happens. But the thing is, what is interesting is what if we talk about the continuous wave that we have been using all along, and that is the sinusoidal waves. So when it's a sinusoidal, you don't really care it's flip the phase or not. I don't care. But in overall scenario that you are getting, it's going to be like you have two waves that is actually traveling in the opposite direction. Does that make sense? So you have one going from left to right, and the other one go from right to left. And they're just going in the opposite direction, and is eventually they are going to interfere. So this one just get back to the original setup that we saw. Just when you have two waves meet at one point, and then you find the resultant wave through the superposition principle. Now we are going to try it and see how it goes. Okay, so first, let me give the first wave to be a sine kx minus omega t. You guys with me so far?
Okay.
Everyone knows how to read this one. Amplitude is a, the wavelength is in the k, the frequency is in the omega, the negative sign mean is traveling in the positive x direction. Good. Now I do the same thing for the blue, same amplitude, same wavelength, but now I have this blue curve traveling in the opposite direction. So I have to put the plus sign in it. Okay. And then I don't care about the phi or not phi. I mean, you can put it on there or not. I mean, that's up to you, but that's, I mean, let's say that I have exactly two waves generated, and then they're just passing each other. Okay. All right. So now what are you getting here? But then you already talked about this one, the final wave. Let me put a sigma on it, even though you don't need to. It's just y1 plus y2. Just add them, Madan. Let's do it together, right? We have a common factor A come out. Psi, when you have addition of psi, you can put it in a product, cosine and sine, with the factor of 2 in the front. And the cosine is going to be the cosine of the difference over 2. Okay, oh, let me move it on the left so I have more space there. There you go. All right, so what I have here is going to be the difference. So sine k minus omega t, kx plus omega t. So let me put it on there. Kx minus omega t minus kx plus omega t divided by 2. So far, so good. That's the cosine term. And the sine terms, the argument will be the sum over 2. I just take the kx minus omega t plus kx plus omega t and then divided by 2. So far, so good. All right, let's smooth things out a little bit here. So the subtraction will eventually cancel this and that. Oh, cancel too much, sorry. This and that. So the kx would disappear from the cosine terms. So what you have is just a negative omega t, right? You have negative 2 omega t on top divided by 2, so the 2 cancel. So what you having here is going to be cosine omega t. Cool. So far, so good.
Okay.
Now look at the sine term over here, guys. So the sine term is going to be sine. Now you sum together, the omega t will get canceled instead in this case. And then you have kx right there. What do you see? There's nothing to celebrate here. What do you see? Whoa. Well, then this is kind of weird, right? What you have at the end is, well, it doesn't have like the kx minus omega t terms anymore, even though you know this must be a wave somehow because you got it from combining two waves together. Is still a wave. But the structure of the function that you're looking at looks a little weird. When I say look a little weird, it's this. Let me rearrange term a bit. So 2a, let me put in the sine kx in the front and cosine omega t in the back. I haven't done anything. Okay, so what you have over here is, now think about it, guys. This is a wave on a string. And this string is being fixed on both ends. Okay, listen carefully. It's fixed on both ends. So what does it mean? It means if you are at left end and the right end, there will be no displacement on the string. Does that make sense? Because it's being fixed. Yes.
Okay.
But this equation doesn't have that yet. This is just two waves going against each other and then just try to, get going forever. This one doesn't incorporate that conditions of having zero displacement at the left end and the right end just yet. So what can I do? Let's impose something to it, guys. So let me put a coordinate so we can deal with this a little bit better. So let's say this string has the length L, and this one is x equal to 0 is on the left, so x is equal to L on the right. Okay, I'm gonna use this coordinates. So what you have over here is, well, John, that's no big deal. It looks like your equation looks good. At x equal to 0, you plug in the 0, sine 0 is 0, so good. The total wave at this point is 0 no matter when, no matter what happens. Time is inconsequence because the sine kx automatically give you 0 every time. Cool. So this one seems okay. All right, so I'll keep that. Now let's pay our attention to the right side of the ends of the string, the ones at x equal to L. What happened when x equal to L? So you plug in into it, what you get is y total is 2a sine kl cosine omega t. What do you see here, guys?
Okay.
Well, Ajahn, this will never go 0 all the time. Because don't forget that the time will keep running, right? Time is 1 second, 2 seconds, it just keep flowing. It never stop as well. So time just can change. So the cosine omega term will just fluctuate in value, up and down, up and down, up and down, right? So this one will go between -1 and 1, just oscillating back and forth, back and forth. So, Ajahn, how can we make this 0 at all time? Can you guess? Because at x equal to L, you cannot have any displacement as well. And this is where the fun begins. You cannot do anything with the cosine omega t term because there's time built into it. So you cannot turn this into 0. You cannot force the time, right? So the only thing left for you to force is the first term that you have left here. Of course, 2a, you cannot do anything with it. It's just a constant. So the only playable items over here that you can still sort of like, do some funny business with it is this dude over here, guys, the K. The wavelength that's built into this K is the only thing left for you to play with. So how can you deal with this? Well, Ajahn, the only way that you can make this 0 at every value of t, you have to make sine kl to 0. Cool?
Okay.
Nobody cares. Okay, just get on with it. All right, so sine kl is equal to 0 when? How can you manipulate this one, Ajahn? That's good. You just have to take the kl and set it to be the multiple numbers, a multiple value of pi, because we know sine of multiple of pi is always 0. And that lead you to the conditions on the K. So what you get over here is K must be N pi over L only. If K doesn't meet this condition, it won't work. Cool? And what does it mean? Let me give you even easier for you to look at. So let's follow the arrow up here. Because K is 2 pi over lambda, I set this to N pi over L. Pi cancel. Now I try to figure out the lambda. Follow my arrow here. The lambda is going to be 2L over N. And where the value of N start from 1, 2, 3, 4, 5, on and on. Right? Because that's where the KL must be equal to. It could be, I mean, it cannot be 0 anymore, because if it's 0, then it's nothing for you. So you start when N equal to 1, N equal to 2, N equal to 3. So what do you see here, guys? So it means there are only some value of wavelength that you can fit into this setup. Isn't that wow thing? So what I'm saying over here is, once you set up this system, which is to say you have two fixed ends, not all of the wavelength can be moving in here. Only the wavelength that fit this condition right here allows to be traveling back and forth in this system. Isn't that cool? And what are those? When N is equal to 1, okay, let me try that. I can call this like lambda 1. So lambda 1 is 2L, lambda 2 is L, lambda 3 is 2L over 3, on and on and on. Now I'm going to draw something and then I'll show you what it is. Let's start from the first. Look at the first. Okay, let me use the yellow here. When the lambda is equal to 2 times the length of the string, what does it mean? It means the wave has to go that long to get the one wavelength. That you guys with me? That's one full cycle of wave. But of course, for us, I mean, we don't want to extend beyond x equal to L. So that's what is going to show up on here. Oh, missed it. Sorry. See, half the cycle is being fit in this string. And in reality, the string is just going to oscillate up and down, up and down, up and down, right? And that's what it is. When it's up and down very quickly, it's going to display this kind of form of the oscillation. And that's the loop that's coming out like this. Whoa. Okay, you got that one? So the visualization is actually, to me, it seems like it's easier for you to think in terms of the string, because the string actually is a physical stuff that oscillating in front of your eyes. And then you can actually observe the actual loop that coming out from the movement of the string quickly. So you can see it as a loop. Isn't that cool? All right, now, Bojan, what about other possibility? Okay, let's take a look at what happened when the wavelength is exactly 1L. Wavelength is equal to 1L is this. You fit one wavelength into that length L, and when it's oscillating quickly, you're gonna get something like this. Does that make sense?
Okay.
And now you start to play a game here, Ajahn. That's kind of like, okay, that's not bad. If I look at the case when the wavelength is 2L over 3, what does it mean? It means you can fit 3 loop, or I mean, it's just like the lambda is just 2L and then you divide it by 3. So you take twice the length and then you divide it by 3 and then you fit it into this length. So over here, so you're going to get some like this. There you go. Okay, so that's the wavelength over here is 2L over 3. Yeah, 2/3 of the whole length here. And once it oscillates quickly, you generate a loop that looks like this. It looks colorful now. Yeah, it's kind of beautiful.
Okay.
But I hope you get what I'm trying to display here is just saying that when you have the condition at the end point, not all of the value of the wavelength can be fit into this system. Only some of them, and some of them mean it has to apply, I mean, it has to adhere to this rule. Lambda is 2L over N is, I mean, these are allowed to be into the system. The rest, it won't work. because it won't fit the condition that two ends has zero displacement at all time. What we are looking at over here is we call it a standing wave, guys. Welcome,
Okay.
standing wave. Why it's called standing wave? Because when you look at this one, there are always some portion of the wave, some portion of the elements inside the medium that does not move at all. See that? At least you can see the obvious two, the endpoints. These are always no movement, definitely no movement. But if you look at the one, let's look at the blue. The blue is a kind of obvious one. This point and this point, see that? These are the point where you always get zero displacement no matter what. Everything else is just oscillating, going crazy. But 1, 2, 3, 4 for the blue waves, these 4 points never move. That's why we call this a standing wave, because it looks like it's standing. It doesn't seem to have anything moving. It's appear to you, it's just like oscillate up and down, up and down. It doesn't like anything like traveling. So that's why they call it a standing wave. Okay. And the point that indicate the zero displacement of the elements of the medium, we call these nodes. Nodes. N-O-D-E, nodes. Okay. So you can use this N for it. So these are the nodes. Okay. And halfway between these nodes, it's just going to be the position where the oscillation of the medium going the highest, right? That's where like, okay, things go crazy. And those are going to be the antinode. That's a name. And then you can use A for it. So this means you're going to have halfway between nodes, it will be antinodes. And halfway between antinodes, it will be nodes. Okay. And now once you sort of understand this whole setup, sort of taken from waves on a string, now we can come back and understand what is going on with the wave that we are discussing, which is sound. Good thing about this one is we already mentioned like back 2 weeks ago when we study waves at the beginning, we're saying that it doesn't matter if the wave is going to be transverse waves or is going to be longitudinal waves, the mathematics using the same form, which is in our case, sinusoidal function. So what I'm saying is when you apply the sinusoidal function, it could be explaining the medium that oscillating in the vertical directions, or it could be explaining the elements that oscillating in the horizontal direction. The mathematics are exactly the same. Does that make sense?
Okay.
Yeah, so that's a good thing is once you understand what is going on a string, which is easier for you to relate with, then you can now turn your attention to sound. And then we're going to have a system that can generate a standing wave in sound. And it's just simply an air column. When you think of the air column, it's just a tube. And that appear in like some piped instrument, yeah, a musical instrument that look like a pipe, or you have like organs pipe, or you have like maybe flute and anything that's had like a cylindrical shape, and that can generate sound. And if you notice, one particular shape of that pipe will generate the dominant sound out of it. Does that make sense?
Okay.
And that is actually, you are hearing the frequency of the standing wave created in that air columns or in that tube. That's what we are going to look at right now. Okay, so how can we figure out the possible wavelength or frequency stuff in this sort of like the whole setup over here? So what we want to do is this, right? I try to go slowly over here, guys, because some of you, even though the end point of this one like is kind of simple to apply, but there are very, very complex mechanical stuff going on. It's like that's processes that going on before you get down to the final standing wave in sound. So what I want you guys to do is this. You guys can go to a website. Okay, I think I can put that site in here too. And it's the simulation. And I hope this will give you a better picture of what is going on here, guys. So follow this. It's the allphysics.com, and it's the if you I have this on my tablet here. But anyway, guys, so let me type that in. I hope it's not too long. Okay, so that's good. It's the simulation number 10. All right, guys. So you can hit this. Uh, you can hit this link as well. Oh, is that a link now? Yeah, it should be. All right. So you can try going to this link and then let me refresh. Let me pause first. So this is a very cool. I like this one because it seems like this one is the best sort of like representation of what is going on in the real like standing wave in an air column. And this has a very, very cool simulations or animation going on because it's very realistic here. Okay, let's take a look. So what I can do is I can adjust the length of the tube wherever I like. Okay, and I can adjust the sound wave that I can just send in. So let's start from this. If I don't put anything, I'm just showing you the original wave. That's it. And let me pick like just any numbers in it. Okay, just any wavelength into it, and I just hit run. So this is what happens is you just send in a sound into this tube. Okay, and of course you will get reflection at the ends. So it's just like wave on a string that you get reflection at the end of the string that fixed on the wall. Same thing over here. You might be wondering, well, Ajahn, why sound has to reflect at the openings of these tubes. The reason is because sound is traveling inside an air, right? So the air inside the tube and the air outside the tube represent two environments, or you can think of it like the medium, which is the air, are having different physical properties inside the tube and outside the tube. So every time that light waves, sound wave, water's wave, or whatever waves try to go from one medium to another type of medium, there will always some reflections going on. Does that make sense? So think about it. If you talk about light, when you look through a glass windows, even though the glass window is kind of like transparent, right? But you always see your own reflection a little bit off of that glass. Does that make sense? Right? No matter how you polish that glass until it's super, super transparent, super clean and whatever, but every time that you look through that glass, you always see some of you, your reflection out of it. That's happened when light changing the medium from air to glass. There will be always some reflection accompany that movement all the time. Same thing over here. When you send in the sound, the air inside the air column and outside the air column, you can treat it. You can treat them as different medium. So every time that waves try to go from one type of medium to another type of medium, there will always some reflection. So let me show you that first reflection that's going on. There you go. So when you send in the sound, there will be some reflection coming back. And this is exactly what we just did. See that? I have two waves running in the opposite direction and they're going to meet in between. Okay, cool. So far so good. And this is good because now we're talking about wave that is actually moving. It's not going to get like frozen in time. But then when you look at the bottom two, that is the resultant wave or the sum of the original waves. Do you see what happened here? It's not oscillate, of course, because the bottom two will represent the summation of the two waves above. But then if I try to adjust this, I'll change the wavelength a bit. And then you notice the amplitude of the sum of the two waves. This one I get a bit bigger, yeah? All right, if I move the other way around, and then I try again, this is not so big, right? The sum is not that big. And I'll keep going, do it again. That's actually even worse. See that? So it really depends on which wavelength you pick. It will have the effect on the final wave. See, this one is good. This the bottom tube, see, the sum fluctuating a lot. See, so this is what I'm saying. There are only some value of the wavelengths that eventually will have the good conditions for the interference. And once you fit the perfect condition that we just study, you get the best out of this one, and that is the standing wave. So let me try to hit that one. So I think I kind of know it because I want a full number. So let me put 5 on here. Here we go, 5. Okay, so now that's perfect. So I pick the wavelength to be matching the length of the tube exactly. So the column has a length of 5 meters. I pick the wavelength to be exactly 5 meters. So you look at the figure on the top, you see that? See, it looks like a loop, right? But now you understand what it means. The loop is a visual representation of saying that, hey, you have two things that is going on here. See, it's not like a real loop, but it's just something that is traveling, passing each other, and then you try to represent it using something. But you look at the sum of the two waves. Isn't that crazy? That is the maximum summation that you're going to get out of this system. And this, you are looking at a standing wave. And this is one of the conditions that fit this one. Okay, does that make sense to you guys? Okay, but the reality of this one is this. The reason I like this simulation is because you're probably wondering, John, you always get the reflection every time that the air try to get from one medium to another, right? So what happened to the second reflection? Because when you get the first reflection of the first wall or the first opening, the reflection will get reflected again on the second round, and it will get again and again. And the good thing about this one is this simulation will lead you to that. I can add the second and the third reflection to it. Let me pause and then we'll run again. Oh, it doesn't refresh. Let me see. There you go. It's here. Now, oh, it doesn't show up a lot here. Oh, what happened? Oh, this one is good. There are multiple reflection going on. All right, but anyway, so I don't know where the multiple reflection is happening. Okay, but anyway, the point is, in reality, it doesn't really matter how many reflection you are going to try to squeeze into this one. The main one that you are going to get out of this is going to be the one that fit the conditions that we just analyzed. Okay. However, okay, the condition will be different because what we were analyzing was the wave on a string, but this one is an open tube and the wave that is going to be a longitudinal waves, which is sound waves. So the condition that we're going to impose on this one is going to be different, but the way that you can approach, they are going to be exactly the same. Right. So all you care about is just make sure that you fit the condition of this air column. And once you have that, everything else will follow. Okay, I'll give you an example of how it's done. Okay, let me show you this. Okay, but I hope you can play around with this. And then you have two choices of the air column. The one is one open and one closed. Okay, so this is the possibility of, I mean, I'll show you in the slide here, but you have two choices of the two. It could be one open, one closed, or the other one could be like open on both ends. Okay, and the conditions are different. Okay, let's get back to our slide and see how it goes. All right, here we go. All right, now I hope you start to see what can be sort of like imposed in terms of the boundary conditions. What you saw over there was the condition that I sort of like restrict ourselves with is the condition at both ends. Every time that you have this kind of restriction, sometimes we call it the boundary conditions. It's a condition at the boundary. And this one we said there must be zero displacement at two ends. That's the case of the string. But now what we have is the air column. And because air is just the oscillations, it sounds, it's just the oscillation of air molecules. And because these two have opening ends, so we hope or we assume or we would love to have the oscillation of the air molecules at both ends to be at the maximum. You guys with me? Because these are free molecules. But sure, go ahead, guys. Oscillate, like go crazy. Yeah, go ahead. Try to oscillate as much as you can. That would be nice. So what I'm saying over here is we can assign both ends of these opening tubes to be antinodes. You guys with me? Because that's where, I mean, we want to fit that condition onto this one. And to be able to write that one, all you have to do is just like playing games. How can you start from the antinode down to another antinode? We already said halfway between antinode must be a node. So the easiest way that you can do is just like, okay, John, you just do like this. You have a single node in between. That's the easiest one that you can think. Yeah, well, okay, John, that's easy. However, I can do better. I can give one more twist to it. Start from the antinote. I twist it one more time, but I still landing at another antinote. So what I'm seeing over here is I just introduce two notes in between, which is fine. I still meet the boundary conditions that I want, which means two ends must be antinodes. You can do one step better. You do one more twist to it. I just add extra notes to it, and now you have three notes in between, but you still end with the antinodes on both ends of the tubes. And then this list will go on and on and on. Got that one? All right. So this is kind of cool, Ajahn. This is neat. So once you have that, then your analysis team seems to follow like this. Okay, let's start from the easiest one right there. Oh, the drawing is not so good. Here we go. So what here did you have here is now I have this. And if you extend this one out, just like what we played before, that's one complete wavelength. But over here that you have, you just stop short halfway over here. So that means what you're seeing over here inside this tube is just half the wavelength. So what you have over here is you can say half the wavelength is just the length of the tube. Or the wavelength of the sound here is just going to be twice as long as the length of the tube. So once you get that, then you can figure out the frequency by doing just the regular formula. It's just the speed of the wave divided by the wavelength. So it's going to be V over 2L, and you are done. See that?
Okay.
That's not bad. And then how can you figure out the lambda on the second case? Well, John, just count. Just do the counting. So look at this one is like, oh, okay, John, I can see that. It's like here, you come here, and oh, that's complete one full cycle right there. So what you have over here is, it means your wavelength is exactly the length of the tube. So with that, then your frequency will be just V over L, and you're done. Keep going. See, the end game is simple, right? And now it's just like, okay, that's one wavelength and a half. All right. So if you want to draw it in the loop, like, okay, that's 1.5 wavelength. So over there is mean is 3/2 of the wavelength is equal to the length of the tube. So the lambda is just 2L over 3. And the frequency is going to be V over 2L over 3. I can flip 3 to the top, on and on. So this is it. See? So the end result is simple. However, I don't know from experience that I had in the past, it's just like many of you don't understand where this loop-like figure came from. So that's why I hope by showing you that if you look at the wave on a string, you can actually see a loop happening on the string because it's actual fluctuation of this one. But if you started out by just analyzing the sound directly, I mean, the sound won't give you a loop like this. However, we use the analogy, or you can use the same visualization techniques that you apply to the wave on a string, and you bring it here, and then you try to do the same analysis there. Then I hope you get a better connections with how can you determine the length of the wave, or what is going to be the wavelength that you can fit in a tube a little bit better. I don't know, does that help? I think it helps a little bit. Right. But if you understand this whole process over here, now you understand that to get to figure out what should be the wavelength is kind of easy. See? So that's not bad. All right. And then I think you can play around with this by looking at another type of the air column. It could be like one open and one end tubes. And then you try to do the conditions just like what we just did. However, the condition will be different because at the open end, you always put the antinode here. And now because you can see that this one is a closed tube, so it means the air at this wall won't be able to move. So you're not going to have any oscillations of the air molecules on the closed end of the tube. So you can put the restriction of the boundary condition to be a node at the closed end. And the rest, just draw whatever waves that you can fit. You can go from antinode to node easily by just saying that, Ajahn, that's it. from antinode to node. I don't have to do anything. So from here, you can see that what you're looking at over here is just lambda over 4. You guys with me? It's only like a quarter of a wavelength. So then you say, okay, so a quarter of a wavelength is the length of the tube. So now you can figure out the wavelength is 4 times the length of the tube. See? And then you can play games now because you say you want to start from the antinode, you want to end to another node. You can add extra twist to it. So what I can do is just like, okay, John, let's put one twist to it, but then I still land on a node. That is allowed. This is good. So what you get over here is you're just passing through one extra node in between, which is fine. So over here, you can just say, okay, it's that half the wavelength and a little bit over here. So what you have over here is going to be 3/4 of the wavelength is exactly the length of the tube. So what you have here is it's going to be the lambda is 4/3 L. On and on. See? So the way that you can analyze this one is now is quite simple, but understanding the underlying processes, I think that's more crucial, yeah, about this topic right here. So what you have here is, once again, it's standing waves, okay? Just to make things sort of like, make sure that you understand this one slowly. I don't want to push anything too hard. I think I'm going to stop our lecture today just at this point and then allow you to maybe play around with the simulation a little bit first, and then, come back and then just make sure that you understand these 3 scenarios: the wave on a string, a tube that has both ends open, and tube that has one open, one closed. Okay. And next time we'll sort of like summarize this whole thing one more time, talk about the terminology, like what are the harmonics and maybe some overtones, what are the relationships between the frequencies allowed in these air columns, and then we just finish this whole thing next time. Sounds like a good plan? Okay, just have time for your brain to absorb this whole thing in first. All right, so next time we can speak like, more easily with each other about this standing wave. All right, guys, any questions? Any Dan พูดรู้เรื่องไหมวันนี้พอได้นะ Okay. Already. Okay, so if there are no further questions, I think that is it for today, guys. I'll see you guys on Wednesday, yeah?
Okay.
Okay, guys. Take care. Bye-bye. I'll see you soon.